Good morning, my name is Gioacchino Tangari, I'm from Macquarie University, Sydney, and I'm going to present our paper titled Classification Assisted Query Processing for Network Telemetry. Let's first of all start by introducing network telemetry and how it works. Overall, network telemetry provides a wide range of monitoring information that are essential for securing and managing networks. For instance, for the detection of threats or attacks, for profiling the resource usage in the network, or for measuring the performance of networks. From a high-level perspective, each network telemetry system operates as a query processor. At the top of the figure, we have the operator, who is interested in threat detection or resource profiling. The operator sends a set of declarative commands, which are also called monitoring queries, to the telemetry system. The queries are then compiled and transformed into low-level measurement specifications. After that, the traffic measurements take place, usually in the data plane, and works by expecting traffic streams in real time. This produces a set of raw measurement data, for instance some flow counters, but however, this data needs to be processed to craft elaborate query responses that then are finally delivered back to the operator. Now, this work focuses on the data processing operations that transform raw measurement data into elaborate query responses. So if we zoom in these operations, we see that to transform raw traffic data into monitoring query responses, we need essentially three operations. The extract operation consists in retrieving all the raw information from the traffic, for instance, some flow counters. Then the aggregate operation consists in a set of group by or say aggregation functions such as mean, sum, and so on that are applied on the raw measurement data. And finally, the evaluate operation consists in checking the extracted information against a set of query conditions or predicates. Let's go through these steps with an example, and let's consider heavy hitter query. The first operation, extract, what it does is to retrieve flow byte counts and the source IP of each flow. The aggregate then aggregates this information on the source IP by summing the bytes associated with each source IP address, and finally the evaluate check whether this sum is above a heavy hitter threshold or not. The main challenge in modern network telemetry is that these systems need to handle many queries on short time scale to support high traffic rates, for instance 10 gigabit per second or more, and to process large number of traffic flows. Now, to satisfy all these requirements, the telemetry system should ideally be able to process a vast amount of measurement data using limited time and resources. So the main problem here is how to reduce the cost of processing all this measurement data. If we look at existing approaches, essentially these solutions are system specific. One of the main solutions is to perform part of the data processing in the switch hardware, but this requires sophisticated programmable switches. In this work, we take a different approach for reducing the data processing costs that are involved in network telemetry. The key idea of the approach is to achieve cost reductions by filtering out part of the raw measurement data extracted from the traffic. We refer to this as intelligent filtering. The approach is shown by this figure, and in general, it relies on two key concepts, two main ideas. The first concept is the ability to predict part of the query results from very small samples of the measurement data. We achieve this by using supervised classification. The second concept is then to use the prediction results in order to discard portions of the measurement data that are initially extracted from the traffic. We can illustrate this using the example of a heavy hitter query. So in this case, from the initial set of measurement data, we sample very few byte counts from flows with a given source IP address X. Then the prediction says whether X is a heavy hitter or not. Based on this decision, based on this prediction, say, we can add source IP X to the query results, let's say to the set of heavy hitters found in the traffic, and then discard all the data associated with X. For instance, if the raw measurement data were initially stored in a temporary buffer, this data will be in the end overwritten. To build the classifiers, we rely on a machine learning approach, as shown here in the figure. Essentially, we have one classifier per query. All classifiers are trained on recent monitoring results, and after the training, the classifiers are refined to satisfy accuracy requirements on the query results. We call this refinement phase, validation phase. Let's start by the training. So, first of all, we need to generate a set of data samples that can be used as training datasets. To this end, we adopt two sampling mechanisms. One is suitable for cardinality-based queries, such as queries that are based on count or count distinct operators, and the other one is suitable for queries that are based on other aggregation functions, such as mean, sum, and so on. All the classification functions used in the classifiers are based on logistic regression. The main problem with predicting query results is that wrong predictions can actually translate into errors in the query responses, so they can degrade the accuracy of query responses. To mitigate this effect, we add the validation phase right after the training phase. In the validation phase, we test each classifier using a small dataset, also called validation dataset. For each input record of the dataset, we measure the confidence on the prediction output, which is obtained based on the probability estimates that are returned by the classifier. And then we check if the prediction is correct or not. Then, as shown in the figure, we measure for each level of confidence on the prediction output, here on the x-axis, what's the corresponding level of accuracy on the query results, and we measure the accuracy both in terms of precision and recall. Finally, based on the accuracy requirements of the query, in this example, in this slide, it's 98% on both precision and recall, we set a threshold on the x-axis. In other words, the classifier results are accepted only when the confidence is high and the accuracy requirements on the queries are satisfied. This method builds on the empirical observation, as shown in this figure, that the more the confidence on the prediction output, the more is generally the classification accuracy. To experiment with our approach, we have implemented it as part of a multi-gigabit per second traffic analyzer. Let's spend, first of all, a few words about our testbed. The traffic analyzer runs on a server using a single CPU core. As a dataset for our experiments, we relied on 4 representative monitoring queries. Apart from heavy hitters detection, we have a query for DDoS detection, one for slow loris. Well, slow loris is a slow HTTP attack detection, and one for bursty source IP detection. The traffic traces we use come from KIDA 2018 passive dataset. In particular, we use 60 traces of 1 minute each. About our evaluation, we first of all measure the amount, the ratio of measurement data that can be safely filtered out by the telemetry system. Let's say filtered out without degrading the accuracy of query results too much. Then we measure other benefits in terms of efficiency of the monitoring system, And as a baseline for our evaluation, we actually adopt the standard measurement data processing workflow, which consists of aggregate and evaluate operations on the full measurement dataset. First of all, we evaluate the measurement data filtering. These plots show, for different filtering ratios, what's the query result accuracy. Now, given accuracy requirements of 98% of both precision and recall, no more than 35/40% of the measurement data can be filtered for a slow low-risk detection query, while for a bursty source detection query, we can filter up to 98% of the measurement data without losing too much accuracy. What we observe is that the amount of data that can be safely filtered out really depends on the query type. However, at the same time, for all the queries we experimented with, we found that at least 30% of the data can be actually safely filtered out. Filtering out significant portions of the measurement data can translate into improved efficiency of the telemetry systems. To quantify this benefit, what we measure here is the maximum traffic rate that is supported by the telemetry system. And in this figure, we show the supported traffic rate against the query reporting interval. So this is essentially the period based on which query results are built and delivered to the operator. More specifically, in this plot, we compare our approach, let's say the classification-assisted approach, against the baseline case where standard data processing operations are performed. What we observe in this case is that compared to the baseline, our classification-based, classification-assisted approach can achieve some gains in the supported traffic rate by up to 30%. And this applies in general to all the different configurations in terms of query result reporting interval. Lastly, we measure the query result accuracy based on different training configurations. These plots essentially show the deviations from the accuracy requirements of queries, which are again 98% of both precision and recall. For instance, a deviation of minus 0.02 in the plot means a degradation of the accuracy from 98 to 96%. In the left plot, we focus on the amount of traffic used to train the classifiers, while in the right plot, we focus on the retraining frequency. What is shown in these results is that both settings, both the amount of traffic used for the training and the retraining frequency, have an impact on accuracy. However, the degradations never exceeds 4% in our experiments. To conclude, we can say that this work shows that it's possible to mitigate or reduce the cost of processing all measurement data based on the intelligent filtering of the measurement data itself. And this can be done by employing machine learning classifiers. However, this approach has still some limitations. First of all, in the case of very dynamic traffic patterns, there might be the need to retrain classifiers much more frequently. Another limitation is that the filtering ratios, let's say the amount of data that can be safely filtered out, really depends on the query sensitivity. For instance, on the threshold used to say whether a source IP is a heavy hitter or not. One more limitation is that the current experimentation is limited to CAIDA 2018 traffic traces. So we plan for the future to extend the experimentation both to a wider set of traffic traces and to a wider range of different monitoring queries. So I hope you enjoyed my presentation and thank you very much.